Three-phase induction motors are the most commonly used AC motors around. You'll find them in literally thousands of applications. With the ability to produce a lot of torque, three-phase induction motors typically power large industrial machines used for product manufacturing, processing, and other applications. Their simple construction, relative low cost, and low maintenance are the main reasons for their popularity. In this program, we're going to look at how an induction motor works and provide you with some basic information on the induction process. We're going to start by listing the components that make up a three-phase induction motor. Then, to help you understand how they all work together and the role that each component plays, we'll review the theories of induction and electromagnetism. Next, we'll explain the difference between synchronous speed and rated speed, how the number of poles affect the stator and rotor, and discuss speed-torque curves. We'll define and compare NEMA motor designs, then take a look at the information that is typically found on an induction motor nameplate and explain what each specification means. And finally, we'll take a look at the various types of motor enclosures. Now, at the end of each section, we are going to ask you some questions to review the points that we have covered. Oh, one note before we start. In many applications, the speed of a three-phase induction motor is often controlled by a variable frequency drive. The information we present today will give you a good understanding of three-phase induction motors and prepare you for the next video in our series titled Variable Frequency Drive Basics. Let's get started. Let's start by identifying the components of a typical three-phase squirrel cage type induction motor. Inside the stator frame of the motor are the stator and the stator windings. The stator is made up of a series of stacked, insulated, and compressed iron slices with cutouts or slots through which we run the stator windings. We use stacked metal slices to reduce electrical losses in the system. Centrally located within the stator is the rotor. The rotor is basically a cylinder with an iron core, which is also made up of laminated slices, just like the stator. The rotor has conducting end caps on each end and conducting bars running through the slots in the laminated slices that connect to the end caps. The result is a rotating cage that looks similar to a squirrel cage. That's why induction motors are commonly referred to as a squirrel cage motor. The rotor is attached to the motor shaft. Bearings support the motor shaft, allowing the shaft and rotor to rotate as it remains centrally positioned within the stator enclosure. The shaft transports the mechanical energy created from the rotor to the load, and an air gap between the stator and rotor eliminates any physical contact between the two components. Protecting the components is the enclosure, which consists of the motor frame and the end bells. The end bells contain bearings which allow the rotor shaft to turn freely on its axis. Now, the type of enclosure can vary depending on the motor's application. We'll talk more about the different types of enclosures later. All right, before moving on, here's the first question. What are the two major components of an induction motor? The answer is the stator and the rotor. These components work together to convert electrical energy into mechanical energy. In this next section, we'll talk about how these two components interact with each other to create electromagnetic induction. We'll start with a definition. So, what is electromagnetic induction? Electromagnetic induction is a process in which current is created in a conductor by moving it through a magnetic field, or by having the magnetic field move or change around a stationary conductor. In a three-phase induction motor, the stator produces the varying, or to be more exact, rotating magnetic field needed to initiate and maintain the induction process. And let's look at how that's accomplished. As we described earlier, the stator has a core of individual laminated plates that are laminated together. These plates have slots in them, which allow insulated electrical windings to pass through the core. The stator windings are distributed around the stator in such a way that when current flows through them, the stator produces a magnetic field. To better understand how the magnetic field is produced, think about the electromagnetic demonstration you may have seen back in science class. An insulated copper wire is wrapped around a nail. When voltage is applied across the wire, current flows through it, and the nail becomes an electromagnet. In this case, you can think of the nail as the stator's core and the copper wire as the windings. Certain metals, such as iron, like this nail, have magnetic properties where the atoms are randomly oriented. This random scattering of atoms cancels any natural magnetic field. But when current is passed through the coil of wire, it produces a magnetic field which forces the atoms to align in the nail. These aligned atoms combine to produce a strong magnetic field from the nail. And the same is true of the stator's core. Three-phase induction motors use balanced three-phase power. The phases are electrically separated from each other by 120 degrees. When you apply alternating current, or AC, the flow of electrons reverses direction halfway through the cycle. To understand how quickly this happens, remember that the standard AC power frequency in North America is 60 Hertz. And that means that current flowing through the stator repeats one electrical cycle every 16.6 milliseconds. And that's faster than the blink of an eye. Here's an example of a simplified model. You can see that the stator is mechanically stationary, but when we combine three-phase alternating current with the correct placement of the stator slots, we create a rotating magnetic field. Now let's look at the rotor and see what role it plays in the induction process. The rotor, with its iron core, conducting bars, and conducting end caps, is constructed to conduct electromagnetic current. As the stator's magnetic field rotates, it induces voltage in the bars of the rotor. As the rotor bars are shorted at both ends using end rings, there is now a closed path for the flow of current in the rotor bars. This, in turn, aligns the atoms in the iron cores of the rotor to produce its own magnetic field, which opposes the magnetic field produced by the stator. This happens because any induced electromotive force always produces current that opposes the force of the source magnetic field. So, the rotor's magnetic field opposes the stator field, which causes it to repel from like poles and attract to opposite poles. This causes a constant chase as the rotor is attracted and repelled by the rotating magnetic field of the stator. We've covered the stator and the rotor, and we have seen how each has their individual function in the induction process. But for induction to take place, there's a third element needed, and that's relative motion. Generally speaking, relative motion is a calculation between the speed of one moving object relative to the speed of another moving object. In this case, the relative motion between the rotating magnetic field of the stator and the rotating rotor. As you can see, the rotor rotates slower than the stator. How much slower depends on the motor's external load and how much energy is lost internally from friction, induction leakage, and other causes. Now, here's another question. Is the rotor connected to the three-phase incoming power? The answer is no. The stator creates a rotating magnetic field which induces a voltage in the rotor bars, which are shorted on the ends. That allows current to flow in the rotor, which then creates its own opposing magnetic field to the stator field. The difference between the speed of the magnetic field and the speed of the rotor is called slip. To help you understand slip, let's take a moment to define some terms that you'll need to know as we move forward. The speed of the rotating magnetic field in the stator is called synchronous speed. You can calculate synchronous or sync speed by using the formula 120 times F over P, where F is the frequency of the AC power supplied and P is the number of motor poles. We'll talk about motor poles in a second. So, with some simple math, you can see that a 4-pole motor connected to a 60 Hz power source would have a sync speed of 1800 RPM. The mechanical speed of the rotor is called the rated speed. A rated speed is based off a motor's rated load. You can usually find the value for the rated speed on the motor's nameplate, indicating the general speed of the rotor at a rated load. Using our previous example of a 4-pole motor running on a 60 Hz supply, the rated speed would normally be between 1725 and 1750 RPM. So, as you can see, with AC induction motors, the rotor always rotates slower than the magnetic field of the stator. The difference between the sync speed of the stator's rotating magnetic field and the mechanical speed of the rotor is called slip. The amount of slip depends on the amount of the motor's load. The greater the load on the motor, the slower the rotor turns in relationship to the stator's rotating magnetic field. The more this difference increases, the more slip increases. To illustrate slip, pay attention to what happens to the speed of the motor as the load is increased and decreased. You can see that as the motor load increases, the mechanical speed of the motor decreases, and as the load is decreased, the speed increases. This increase and decrease in motor speed due to load is called slip. Well, let's take a moment to review. Now, here's another question. Is the rotor's speed the same as the stator's rotating magnetic field speed? No. The rotor's speed is always slower than the rotating magnetic field of the stator in a positive torque application. If both were traveling at the same speed, there would be no induction and the rotor would not be able to create a magnetic field. Induction motors can be constructed to handle various loads and various speeds. One way is to change the number of poles in the stator. You can increase or decrease torque by adding or subtracting the number of poles in the stator. The more poles there are, the slower the magnetic field rotates. Using the sync speed formula, we can explain why that is true. Revolutions per minute equals F, which is the motor's supply frequency in Hertz, times 120 divided by the number of poles. So, say you have a 2-pole motor powered at 60 Hertz. 60 times 120 equals 7,200. 7,200 divided by the number of poles, in this case 2, shows us that the stator's magnetic field will rotate at 3,600 revolutions per minute. But what happens to the motor's synchronous speed if we add more poles? If, like the example just given, the motor is powered at 60 Hertz and we have 6 poles instead of 2, the synchronous speed produced by the stator decreases to 1,200 RPM. You can see by this table that sync speed decreases as you increase the number of poles. So, high-torque induction motors have slower sync speeds and lower torque motors of the same size have less torque and higher synchronous speeds. One thing to note, as pole count increases, so does the cost of manufacturing. So most induction motors are 2- or 4-pole configurations. If more torque is needed, most people will opt for a physically larger motor instead of using a 6- or 8-pole machine. Well, it's time for yet another quiz question. If we have a motor with a rated speed of 1,774 RPM, how many poles does it have? And the answer is 4 poles. We know that our rated speed is going to be a little bit less than our sync speed. Looking at this table from earlier, we see that a 4-pole motor has a sync speed of 1,800 RPM. This tells us that if we include slip, we are around 1774 RPM. In this next section, we'll discuss speed-torque curves and what they mean. Induction motors are used to produce work or to complete a physical task. As they work, induction motors use electrical energy to produce the torque needed to accomplish that task. A speed-torque curve shows you how the torque produced by an induction motor varies throughout the different phases of its operation. Starting torque is the amount of torque an induction motor produces as it ramps up from a standstill. Looking at this example of a speed-torque curve, we can expect the starting torque to be about 150% of rated torque. Pull-up torque is the amount of motor torque available as the motor accelerates toward its rated speed. If the motor's pull-up torque is less than the amount required to accelerate the load, the motor will never reach its rated speed. As the motor continues to accelerate toward its rated speed, it encounters its breakdown torque. Breakdown torque is the greatest amount of torque a motor can generate. When the motor has accelerated itself to its rated speeds, the motor should be producing between 80 to 100% of its rated torque. That is, of course, if the machine has been designed properly. Now let's look at our example again, but this time let's pay close attention to the motor torque. As the load is increased and the motor's speed decreases, the amount of torque produced by the motor increases. Watch it follow this line. You can see that torque and current are proportional. That means an induction motor draws more current as you increase the load. So, as the load increases, it increases the amount of current that the motor draws and, consequently, the amount of motor torque produced. Okay, let's look at another example. Let's say the machine load gets very large, so large that it causes the motor to produce torque near the motor's breakdown torque rating, and then beyond it. You can see as the load increases, the amount of torque increases and follows this curve. Because of this, the speed of the motor begins to decrease and the amount of current flowing to the motor increases. Current flow in the rotor begins to decrease as the rotor becomes saturated. This decays the rotor's magnetic field and causes the motor to slow down or stall. Even though the current is decreasing in the rotor, the current in the system as a whole is going to increase. When the motor slips beyond its breakdown torque, it begins to produce less torque, which then causes the motor speed to decrease even more and in many cases stall. This situation usually results in damage to the motor if left in this state due to overheating of the stator. Though typically there's an overload relay that will protect the motor from damage. Well, here comes another quiz question. If we look at the speed-torque curve, at what point is the torque at its maximum? Did you come up with breakdown torque? I hope you did, as breakdown torque is the greatest amount of torque a motor can generate. Now let's discuss the NEMA design types and why they are important. An organization called the National Electrical Manufacturers Association, or NEMA, establishes technical standards for the manufacturing of electronic products. NEMA has established standards for 4 different designs of electrical induction motors, which are A, B, C, and D, respectively. Each standardized design has unique speed, torque, and slip capabilities depending on the work they perform. NEMA Design A motors are allowed a maximum slip of 5%. They are similar to Design B motors in respect to torque output. However, these motors are not limited on their starting current. This allows for lower winding impedance, which in turn lowers stator resistance, making Design A one of the most efficient motors from an energy standpoint. Design A motors often offer greater breakdown torque than Design B. Centrifugal fans and pumps are typical Design A applications. NEMA Design B motors are the most commonly used induction motors in the industry. They have a maximum of 5% slip and speed-torque characteristics that are similar to Design A motors, but with a NEMA-mandated limit to their starting current. Because they can provide good pull-up torque, Design B motors are used in a wide variety of applications. Design B motors can also take impact or burst loads at full speed without stalling. Applications using NEMA Design A and B motors are best suited for drives, a topic that will be covered more in our next installment with Drive Basics. A NEMA Design C motor also has a maximum of 5% slip. Design C motors are built to power equipment requiring high breakaway torque, like positive displacement pumps and conveyors. Similar to Design C motors, a NEMA Design D motor is a squirrel cage motor designed with a maximum slip of 5 to 13%, low starting current to withstand full voltage starting, and very high locked rotor torque. Like Design C motors, you'll find Design D motors powering equipment with high starting torque requirements like cranes or hoists. Design D motors are also well suited to high impact loads applications like stamping presses. All right, before moving on, here is another review question. Which NEMA Design motor will be the best for a fan or pump application? The answer? Design A and Design B are both suitable for this application due to their low amount of slip and high breakdown torque. In this next section, we will give you an understanding of the information on an induction motor nameplate. In North America, NEMA also establishes the standards for the information provided on the nameplate. This information is vital to determining the motor's characteristics. Let's look at a typical nameplate. Horsepower is a measure of the motor's mechanical output rating and its ability to deliver the needed torque for the required load and at the rated speed. You can calculate horsepower by multiplying the motor's speed times the amount of torque in foot-pounds and then dividing that sum by 5,252. Torque is a measure of the turning or twisting force supplied by the motor to the load. To calculate torque in foot-pounds, multiply horsepower times 5,252, which is a constant obtained by dividing 33,000 by 2 pi, and then dividing that number by revolutions per minute, or RPM. Motor-rated voltage is the optimal performing voltage of the motor. Because line voltage fluctuates, motors are rated with a 10% tolerance above or below the rated voltage shown on the nameplate. Motor-rated current, which is listed on the nameplate as FLA for full load amps, is the amount of amperage the motor needs when it is operating at full load torque and horsepower. The motor-rated frequency is the frequency at which the motor is designed to operate. In North America, the rated frequency is 60 Hz. Some motors are designed to work with a variable frequency drive, or VFD. They are rated to run at different frequencies. Motor-rated speed, or full load RPM, is the approximate RPM at which the rotor is rotating when the motor is operating under full load. Motor-rated speed is expressed in revolutions per minute. Motor poles indicates the number of poles inside the stator of a three-phase motor. Motor phase is the number of AC power lines supplying the motor. Of course, with a three-phase motor, there are 3 power lines. The NEMA design letter indicates the motor's NEMA design type, either A, B, C, or D. The letter designation describes the motor's torque and current characteristics. Insulation is crucial in an induction motor. The insulation class describes the thermal tolerance of the motor windings. The letter indicates the motor winding's ability to withstand operating temperatures for specific lengths of time. Motors controlled with a variable frequency drive and/or motors that run at lower speeds usually have a higher insulation class. Service factor represents the percentage of overloading a motor can handle over short periods when operating at rated voltage and frequency. The frame size describes the mounting dimensions, including the foot-hole mounting pattern and shaft dimensions. Now it's time for a question on nameplates. What is usually given on the motor nameplate, synchronous speed or the rated speed? Rated speed is usually given for a motor. With this, we know how fast the shaft is spinning at the rated load and can easily figure out the synchronous speed if needed. Standards have been established by NEMA for the types of induction motor enclosures. The standards are based on the motor's use and are designated on the nameplate as ENCL. An open drip-proof or ODP enclosure is typically used for indoor applications. The open drip-proof enclosure allows outside air to circulate over the windings while preventing any liquid from entering the enclosure within 15 degrees from vertical. A totally enclosed, non-ventilated, or TENV enclosure uses cooling fins to dissipate heat instead of a fan or vent opening. They're designed for installation indoor or outdoor in dirty and/or slightly damp conditions. A totally enclosed fan-cooled, or TEFC enclosure is cooled by a motor shaft connected to an exterior fan. Though they're not waterproof, TEFC enclosures are used outdoors in dirty locations. And the final type is a totally enclosed blower-cooled, or TEBC enclosure, which is cooled through forced convection by a rear-mounted blower. You'll find TEBC enclosures in both indoor and outdoor applications. Other types of induction motor enclosures include totally enclosed air-over, totally enclosed washdown, explosion-proof enclosures, and hazardous location enclosures.
Young English Engineer. Your way to the electronics world. Like our Facebook page and learn more. Project provided by Tesla Institute. School of Electrical Engineering and Automation.